All right, anything else?
Kind of along the lines of potential innovations, but specifically with batteries and electric cars, like what the future is looking like for that.
Yeah. All right. Anything else?
My favorite is always use of renewable energy for rail propulsion, whether it be RTD, intercity passenger trains, or intercity freight trains. Just an overhead chat.
Okay. Okay, maybe one or two last ones, and then we'll go ahead and get started. And maybe another question would be, why is transportation kind of such a big deal? We have some indication why that's the case. Way back at the very beginning, we looked at the energy flow charts from Lawrence Livermore, and we saw that transportation was kind of a big part of what it was in it from an energy picture point of view. So that's maybe one motivation. Anything else you could think about for topics tied into transportation, perhaps? Yep.
Like kind of a distribution of like what's actually being transported, like humans versus like
Sure.
cargo and stuff. And like how we can optimize that.
So again, we see freight is a common application. Moving peoples is a common application. And so all the different choices I have in that would be something that I might be interested in looking at. This was a slide that came out of when we taught this about a decade ago, but it's still largely true. If you take a look at a car as being maybe the piece of transportation to think about the most, is then you start thinking about why we've got inefficiencies. We really focused on inefficiencies of thermal engines for generating electricity. When we looked at the Livermore diagram, we saw these big gray boxes that correspond to losses. And they were almost all because of the use of coal-powered steam engines and natural gas-powered turbines, things like that. But then I start focusing on something which has aspects of that inside of it. So I'm using gas inside of a traditional car. But what are the other losses of energy? So this is always a nice picture that I've liked, because it sort of highlights the things that you can maybe fix or not fix. It's becoming more and more common to have battery-powered vehicles. But then
Can you share your screen, please?
thank you very much, Sam. Can you see it now?
Yes, thank you.
Thanks for mentioning that. Okay, so again, I can think about things that I could possibly enhance on this, and some of the things that you see in the reading literature about what's been improved in transportation will actually address a lot of the pieces inside of here. Things like, for instance, this is the one, the energy and chemical or electrical would be losses tied in with that. That's one we can maybe fix. How about losses in terms of braking or aerodynamics or engine losses or other pieces? What are the pieces we can kind of fix? So that's part of what we'll look at, tied in somewhat with those things. I'm going to be using this reference a fair amount. And let's see. I always forget how to fix this. Okay, so this is a book that's got a 2020 publication year. It gets renewed every now and then. There's a reference for it at Oak Ridge National Laboratory. And a lot of the figures, the new figures you'll see are coming out of this. Many of the things that we are interested in transportation are sort of the numbers, because we know broadly why we're interested in things. Okay, so this was my first slide, sort of in the why transportation matters. And the things up top maybe are meaningful or not so meaningful. If you look at the carbon dioxide emission, which is driven a lot of what we've talked about energy, is you can see that in the last 30 years, there's been a change. In some places more than others. So China has dramatically changed with respect to CO2 emissions, and that's not too big of a surprise. If you look at the United States, we're relatively flat. And again, you might have guessed that also, because you remember that when you look at the Lawrence Livermore energy picture, we're relatively flat at about 100 watts for the last couple decades. And because we haven't changed the mix of energy that much, then probably the amount of CO2 we emit is pretty constant. So again, that's not too big of a surprise. The thing which maybe jumps up is if you look at the lower part of this and ask, what can we do about the CO2 emissions? And the thing you realize is looking as a function of time is that it's gotten worse. If we take a look at the percentages of carbon dioxide emission from fossil fuels and the part that comes from transportation, it's gone from about 30% to almost 40%. And again, if I think about which part of it is actually from gasoline, the cars that we drive and the things that are on the road, that's about 60%. Now, maybe a question before we move on is, why do you think it's gotten worse? So if I look at this number, the 31 to almost 40, why has the fraction gotten higher?
It's called the VMT, vehicles miles traveled, has gone up
Okay.
significantly, I believe.
Yep. So we can take a look at that. And so if we had the same efficiency of the vehicle over the 30 years, we travel more miles, then the amount of CO2 we generate in the vehicles would go up. But because total staying roughly the same, that means it has to be offset by a second part. So David's point is good, is that when I take a look at the amount that I generate from vehicles, it might have gone up, but there must have been something which went down at the same time. So what's perhaps gotten better in the last 30 years?
Quality of the fuel.
The quality of the fuel, some efficiencies. When I look at the power plant generations, that switch over to natural gas has improved things significantly. And even the better quality of the fuel that I have associated with it. So that's kind of for me, the big reason when I think about the transportation impact is, again, the CO2 largely reflects not just climate change, but also a lot of other factors, one of them being air pollution. So if I take a look at emissions, forgetting about CO2 and climate change, and the other parts, is that I also think transportation plays a large role in terms of other things that we consider to be part of pollution. Carbon monoxide is a predominant one. NOx, nitrous oxides, it's also very, very large. Volatile organic compounds, VOCs, so unburned gasoline and fuels of different sorts. They're often cleaned up inside of a power plant, but in a vehicle, they're much more difficult to deal with. Maybe the other two, which are not surprising too much, with the sulfur dioxide content, there's a reasonable amount from transportation, not a huge amount though. But again, it has to do with typically in a vehicle, my ability to clean up the waste gas is a lot less than inside of a power plant, where acid rain has been something they've been dealing with for decades now. PM is particulate matter. And again, if I think about vehicles and their contributions to it, not just in the fuel stream, but also the movement inside of it. So when you look at air quality standards, particulate matter 2.5 is one of the air quality indexes that's been looked at. And again, we're getting some fraction of which is coming from transportation. So I'm looking at the contributions of fuel to the CO2 and climate change impact. I firmly believe that they're related to each other, and also overall pollution. In the graph that we saw before from Lawrence Livermore with Engy flows, we could have gotten this out of it also, but I just pulled more recent data. So the 2020 Energy Information Agency, transportation is about a quarter. It also isn't very efficient. So the overall efficiency, when I take a look at it, like we saw on the very first slide, is 20% tops. When I look at the percentages or the breakdown, passenger vehicles correspond to almost 2/3 of it. And so that's something which, at the very end of the last class, we talked a little bit about that, is if I take a look at the energy costs of the different forms of transportation. There's planes, vehicles, freight, and there's overlap between all of those to some degree. But if I look at those and think about which one would be most significant, which ones can we try and fix to improve things, passenger vehicles turns out to be the biggest. From the first page, we saw things that we could possibly alter. We were talking as one of the things on the sideboard of what could be better for the electric vehicles. Which ones of those actually improve? So how about vehicle weight? Is a Tesla lighter than a normal vehicle? Not by much, right? Your call. We'd have to, I don't actually know what the answer is, but the battery packs are pretty heavy. And so we know there's a contributing factor, which maybe doesn't improve that too much. Aerodynamic drag, the front side of a Leaf or of a Tesla S, they're not a whole lot better. So there's no significant change with respect to that. Heating losses in the engine. How about that one?
Less.
Should be less,
There's
right?
no engine.
Right, well, there's an electric motor. Electric motor is about 90% efficient. Electric vehicles don't have radiators, so they have no need to dissipate heat. So the heating loss is improved. Rolling resistance, probably about the same wheels, same tire pressure roughly. How about braking losses?
It depends if you're using the, yeah, it depends if you're using the brakes to help recharge the, some Teslas have that.
Yep. So most electric vehicles have regenerative braking, and again, it also has standard disc brakes on it as well. So you can get some reduction in braking loss depending on your driving style. And driving speed and amount of idling. How about that?
I mean, just idling, it's not, it's different, like you're not burning gas.
Yes. Yep, so one big advantage of an electric vehicle is that when you stop, other than the control electronics inside the system, there's no power being drawn. It's very, very small relatively. So if you look at the energy draw, just running instrumentation inside the vehicle, it's very low. As opposed to a motor vehicle. So in the case of a motor vehicle, when you're running down the road, you're probably doing 1,000 RPM, you idle more around 800. So you're still doing about 80% of the energy draw. In the case of a gas vehicle just sitting in a light, compared to an electric vehicle, which is almost none. So we do get some definite advantages with respect to electric vehicles. Other piece to take a look at. This is kind of nice because it also gives me a sense about what the distribution is in terms of what the vehicles are that are consuming fuel. As an example, jet fuel is 9%. And so that means that if I take a look at the mix, just based on the amount of fuel that's expended, I would maybe get some savings by improving airlines. But again, it's not nearly as large as if it improved cars. The other thing this points out is biofuels. Last class, we talked a little bit about that. As I mentioned, I ended up switching the order from what I originally thought we would do, because that turned out to be a fairly important component. Of the biofuels, at about 5%, most of it is ethanol. There's a small amount which is biodiesel, and this is the United States specifically. But again, it's not a very big chunk. It's only about 5% or so. This is probably a better graph for trying to address what we're looking at before, is the breakdown on the different parts. So transportation by mode and use. So if I take a look at the distribution, the maybe surprising thing is light trucks being the largest. Cars, passenger vehicles, and motorcycles are going to be pretty sizable. The trucks are fairly high, light trucks. Other trucks, I don't know what the cutoff is for that. Look at the top three, we've got 30 plus 40 something. So about 3/4 are in those top three categories. Aircraft, as we saw in the last graph, jet fuel was about 9%. Aircrafts were about 8%. Boats and ships, the water vehicles. And again, this is for only within the US. So international shipping isn't taken up as part of this, I think. Trains and buses, military, and a couple other categories. But again, I can see the biggest impact I'll have is looking at trucks and cars. Now, if I do the comparison with the world, this again is the other agency, IEA versus EIA. And their plot, again, from 2018, shows that, again, I'm really dominated by vehicles. So all the stuff in blue corresponds to road type transportation. On the outer ring, it's broken down a little bit, and it says if I look at passenger cars, that includes light trucks is a big chunk. There's the next biggest chunk, about a quarter by eye. Looks like freight transport, so larger trucks. Buses and motorcycles are small contributions in that mix. If I look again at the amount that goes into water, rail, and air, still relatively small numbers. We had 8 or 9% for the United States. There is about 7% for the world. So somewhat similar to that. But again, I think about work and I possibly have a big impact in terms of transportation and energy use. It's probably in cars and trucks. This is another graph. Again, as I said, these weren't in last year. I really like these because you start to look at the distribution of vehicles as a function of the country that you're within. And so the plot, I superimposed the characters in the actual picture in the PDF. There's a little corner that was cut off in another figure. So what you're looking at here is as a function of time for the straight line going upwards. That's the US. So the number of vehicles per 1,000 people for the United States. Now, if you look at the points on it, they correspond to different countries and they identify the year. Because it kind of makes sense if you look at the growth of automobiles. In the 1900s, there's none per 1,000. And then as Ford start coming online and vehicles increase, the United States by the Great Depression, someplace around there are about 200 vehicles per 1,000 people in the United States. So 1 per 5, roughly, so 1 per family, ballpark. And again, that includes all the trucks and other things like that. So that doesn't mean that every family had a car. It just meant on average, when you look at the vehicles, the trucks and other things, there's about 1 roughly per family. And then I moved past that, so I cut off part of it. But again, for the US trend, going up to 2018, the last year that's on it, there's about 1 per person in the United States. Okay, now let's see how the other countries compare to it. So here's Mexico in the same time frame, and there it's about 350, so about a third of the United States in terms of vehicles per 1,000 people. And again, looking at different parts on it, we can see Canada's up about 660, so it's about 3/4 of the US, and other countries like Western Europe are certainly in the same location as well. So it does give us an idea of where things are. By comparison, going down to the bottom part of the graph down here, so the part that's enlarged. So now the scales are 0 to 200 on this side. And if I'm looking at Indonesia as an example, there's 1 in 10, roughly in 2018. India is roughly 40 per 1,000. So 1 in 25, roughly. And so the numbers are a lot less. And so then when I think about what impact overall will I have, I offset India's large population by the fact that the number of vehicles is decreased by a factor of 40 roughly. And I can start to think about what global things can I do. Now, most of the data I'm looking at is actually US data because it's coming from this one publication. But again, you can kind of keep that in mind when I think about transportation and how it's impacted globally. So this one again is kind of a breakdown with all the different forms of transportation, specific to the United States. One of the things that maybe jump out on that collection of data. So the last 2 columns were percentage. Those 2 years are roughly side by side, so there's not a whole lot of change. So I'm not too sure why they do the comparison in that case. But what are the things that maybe would stand out on that? And what is maybe a problem with the data presented in this form?
You just eyeballing it, like. There's like some where the percentages are so like small that like I'm not sure you could, like, the rounding error would be so massive on those. Like
Sure.
probably.
Yeah, so certainly some of the ones down here.
Yeah.
are pretty tight.
Intercity 0.0%.
And maybe what does it reflect? So when I look at the bottom of the graph, looking at the non-highway ones, is passenger rail down here is, like you said, percentage-wise, it's 0.2. And so if I think about the US picture, what does that reflect? The fact that it's so small that it's almost like you said, if I drop this thing big, then I would see that as 0.
Yes, it's or exponentially larger.
It is. The US is fairly large, and so that has an impact. Physically, it's large also, which you would think would favor to some degree rail transport, but it turns out it doesn't. Is that again, it's a really, really tiny number. And to some degree, it reflects the fact that Amtrak is not very common when you think about the way that you travel. And the infrastructure bill that may change. That's one of President Biden's favorite ways of traveling. But at least currently, right now, the amount of rail transport is very, very tiny. So the number back here is small, but it doesn't really tell me about the efficiency of transportation. So is rail a good way to go? Same thing with respect to air. I could see that air is again up at 8-9% like we saw in previous graphs. But I still don't really have a good sense about whether that represents a good thing or bad thing. It just represents that the amount of energy that goes into flying is small compared to the amount of energy that goes into cars and trucks and things like that. So a downside of looking at data in this form is it's not normalized very well. What I'm interested in is what is it per mile per person? So a normalization or an energy intensity would be the more valuable graph in the case of this. Now, before I flip to the next one, what would you say, what would you guess is the most efficient form of transportation if you normalize it by person and by mile?
Passenger transportation.
Passenger transportation, right? Because it'll be different for freight. So good question.
I mean, I know motorcycles are pretty efficient. I'm not sure they're the most efficient.
Sure, that's a good point. Motorcycle seems like it should be pretty good. And by the same token, you kind of go to the direction of what's often called medium mobility, things that are smaller in scale. Yep.
Steel wheel and steel rail has about 4 pounds of force needed on tangent level track.
So rail is low rolling resistance, a little bit of drag, not the most aerodynamic cross section, but it definitely has some advantages with respect to movement as well. So let's take a peek. Okay, so the energy intensities are the last column, last 2 columns, I should say. So again, this is V2 per vehicle and V2 per passenger mile. So that's actually the column I'm more interested in looking at, because now the normalizations are put in correctly, so I can get a sense about what the efficiencies are. So I'm going to move my mouse off to the side. So let's take a look. Looking down at rail at the bottom, as David suggested. If I were to look at that in that column, it's 1,000 BTU roughly. For let's see, going across Amtrak is about 1,500. Transit rail is around 800. Commuter rail is 1.6. So they're all around 1,000 or so. Now I go up and take a look a little bit higher. If I take a look at air, when I'm flying on a commercial route, I'm about 2.5. So compared to rail, rail is a factor of 2 better than air transport is. And then I go up a little bit further and I look at cars, and cars are not as good as airplane travel or as trains. Now, if you're going to take that a little bit further, let's take a look at buses, because you think a bus is sort of like a train to some degree, in that it's a mass transit vehicle. And I look at that, and the answer I get is that it's actually significantly worse. Why are buses so bad?
I feel like gas wise.
You know, gas is some part of it. So in terms of the engine efficiency, it's probably a little bit lower than a car would be. In terms of the number of wheels or rolling resistance is a bit higher.
Well, like, just with bus routes, like with a car, you go from where you need to go to where you need to go and you're done. Buses like have a lot of extra mileage where people might not necessarily need
Sure.
to go there. And they also like start and stop a lot, which I know is terrible.
There you go,
Yeah,
that's,
So that would be an impact, is the
Yeah,
stopping this party would have a negative impact also. Anything else?
What if there's just not enough passengers to make it worth it? Because an airplane is always full for the
Sure.
most part, but a bus, especially like a night route, is rarely gonna have that many people on it.
Yep, so that would have an impact also. So you can kind of see why it is that that's bad. By the same token, so demand response is a category that you can see it's the absolute worst. And what I had to look up what demand response meant cars, vans, and small buses that respond to dispatch calls. So that means the shuttle that takes you to DIA at the airport, the Uber ride that comes in to picks you up. And again, if you take a look at that, it's just awful. Why is it so bad?
It doubles the distance because it has to come get you and then take you.
Yep, doubles the distance. The occupancy is always really, really low. And again, you can see the load factors aren't great. So the load factor is the number of persons per vehicle. I'm not too sure how I came up with 1.1. I'll think about that a little bit. Persons per vehicle. Yeah, that doesn't seem quite right because there's got to be a driver inside of it. So I'm not too sure exactly how that works out. But again, if you take a look at the load factors, you can see the contributing factor inside of it is when I look at those buses, it's 7.7. So it's better by a factor of 5 roughly than a car, but probably the efficiency of the vehicle is worse by at least a factor of 5. And so the jump I see with respect to the BT per passenger mile is kind of a combination of the fact that the load factor is tiny and the vehicle is not quite as efficient. So if I were again thinking about what were the things that I'd try to improve on it, there's sort of 2 things I have to think about. Where are the way places that I get the increase in terms of the energy intensity? Can I make that better? But I also have to look at the total number of miles traveled. Because I know in the end, in terms of raw contribution to making transportation better, I really need to focus on cars and trucks. Because those again are 60% of energy used for transportation. Okay, somebody mentioned the idea of the use of transportation. So this is sort of the slide that relates to that. It depends. Again, depends on what distance you travel. So again, a really nice slide that comes from inside of it. If I'm looking at traveling distance below 100, 100 miles, I have to check that. It's going to go by truck. Okay, and again, by truck, we mean all the Amazon vans and things like that that we see as well. So short distance is dominated by trucks. If I go further out to cross country, I think trucks are still up there, but rail now is comparable to it. And even if I look at water transport, so this is again all domestic. So I guess that's up rivers and up along the coasts. It's not an insignificant one. Looking at 2000, 2000 actually is. Let's see, vertically the U.S. is only maybe 1,500, so I'm not too sure exactly what over 2,000 miles is in that case. But again, we can kind of see a little bit about how do we actually think about the distribution of travel and what freight is used for. And it depends. It depends on how far I'm going. So this is where things get a little bit scrambled. So combining a bunch of different documentations. I just wanted to put this one up because I think it's kind of nice. Partly because we talked about last class. So this number down here, 63, is one I most want to point out. If you look at fuel refill sites, what you'd like to have is lots of places that you recharge your vehicle. And we can see that if I look at the 2020 numbers, electric charge stations, and they don't literally mean electric outlets because they're buildings of electric outlets.
Yeah.
They mean charge stations. So there's about 100,000 charge stations through the United States. And does it seem like a big number or not? Kind of small, right? And if you compare it to gas stations, which I don't know what the number is, but it's gonna be huge. But then you go down past that and say, suppose I do liquid gas, natural gas. How's that look? That's still not great. So 3,000 divided by 50 states, is there 60%? It's not a ton. They're gonna be concentrated inside of cities. So it improves a little bit, but my ability to actually get to a station like that or compressed natural gas is also pretty poor. Same thing with respect to biodiesel. And hydrogen is just hopeless. Unless I'm on the West Coast, there just is no ability to use hydrogen as a fuel. So although hydrogen fuel cells seem like a really promising idea, besides the fact that hydrogen is not green, we produce it from natural gas right now, there's just no infrastructure for it at all. Okay, so this one probably should have been the other way around, but again, when I tend to look at what is it that I would try and do to improve things, stats about what sort of travel people do is also valuable. This is the US, so almost half of the stuff we do is less than 6 miles. So we don't have very, very long distances that we travel. It falls off pretty quickly past that, so 7% is greater than 30. So those long distance drives that people think that they're going to be affording, not as big of a deal. Why is that important? That the majority of travel we do is actually pretty short, about half of it.
Well, like it affects how like our infrastructure is set up. Because like in the previous slide, like if we don't have a ton of charging stations, but you have one next to where you live and where you work, like it's not really a big deal. It's
Right.
You're not going very far. But like, for example, like you can drive a Tesla across Nevada, just there's just not enough charging stations. So like
Sure.
the distance affects how much infrastructure.
Yep. So it does mean that there is a demand with respect to infrastructure that has to do again with distance that I travel. Anything else? The other part, again, this is just focusing on cars and light trucks, is how much range do I need? Because vehicles, the default in the United States is 300 miles. And so that's where electric vehicles were falling short for quite a while, is they didn't have that range. But then when I think about what do I need 300 miles for, I'm looking at the trips out here someplace. And the percentage is actually quite small. So it means if I were to think about how to design a fleet, if I were to start from scratch and trying to decide what the characteristics of vehicles are, 300 miles isn't that big of a deal anymore. Because we don't travel that far. And again, that's sort of reflected inside of here. So 25-ish miles per day is fairly typical of the US. So again, if I were to think about an electric vehicle, then how much range do I need? And again, it depends how many charge stations I have available. So if I'm only driving 25 miles per day, then that means in a week, and presumably I charge up more than once a week. In a week, I'm only doing 175 miles. So 300 is almost double of what I actually need in terms of range for the typical person traveling around. This was, let's see, this one was talking about, again, newest numbers are relatively new. The 2018 numbers in the last publication on passenger miles of different sorts. You can see that buses are still fairly significant in terms of the value of it, as is rail. So these demand response, the Uber type trips are relatively small still. So even though the energy costs are relatively high, improving Uber services or vans running up to the airport doesn't have that much of an impact because the total number of miles associated with demand response vehicles is relatively small. This was actually kind of surprising me though. Is the number of Uber trips worldwide over about a decade. So about 1 billion per year of Uber trips. And so the population of the world is how much? Yeah, so if you just do averages, it's so there's about 1 billion trips per year. And that means that each person takes, well, a 7. It's not quite a factor of 10. But again, a much, much larger fraction than I would have guessed with respect to looking at Uber trips. I included this one mostly because it's a figure after, but what's the value or interest of this? So if I look at the last 2 sets of data, scooter trips is the green. Blue is e-bikes. And there's just a recent article about electric bikes. And then the lower ones are the shared bike things, like in downtown Denver, there's the red bikes that are parked on the side of the streets. So what would you say would be the significance of that? Or maybe what does that tell us about what is happening in the United States?
It seems like something is being replaced with scooters, because like from 2017 to 2018, we added 2 whole
Sure.
chunks like that, and like those had to come from somewhere. Like it's not a big enough thing, so like it probably is either replacing like walking or cab rides or something like that.
Right. Yep, that's a good point. And so there's about 40 million new things got added in because of scooters and e-bikes. What do you think they replace? I mean, that's a great question. Is the total number of trips probably stayed the same, roughly, because the population stayed roughly the same. So if I were to look at for 40,000 trips that are different, and again, the U.S. population is about 300 million, so it's about a tenth every 10 days, a trip or something like that.
I mean, in my experience, they replace people walking, which is a negative net, but they could replace very short car trips as well, which I guess is an improvement.
Yeah, and we saw that about half the trips are small, they're less than 6 miles. But you're right. I mean, if they replace walking, that turns out not to have a positive effect. I don't know the answer, but that's a great question. So I guess the hope would be that these things were replacing things that are further in terms of travel, but they might actually be very short distances as well. They are, for me, they're interesting because it does say that in the last couple of years, there's been a new mode of transportation that wasn't available before. So if you're thinking about, for instance, moving around campus, mine's for a very short time tried a shared bike program. It failed for different reasons, but wasn't too successful. It hasn't tried a scooter program yet. It has tried the rover. And I understand from talking to other students that that's a little bit of a joke on some of the different cat things.
Yeah.
So was a rover a good or a bad idea? And what would be the alternative to it? Because really what it's talking about is coming from Mines Park to here, going to downtown Golden, and the parking lot down by the river. That's really primarily what it does, right? So what would be a better alternative? Yep.
I wish you'd go to the library station.
Yeah.
Oh, it doesn't go to Light Rail Station, does it?
So, I mean, everybody's got to drive from Denver,
Right.
can't take the light rail because it's about 3.5 miles.
Yeah, so a good alternative or a useful thing would have been to be able to go to the Light Rail Station. That's true.
It's also slower than walking.
Yeah.
Is the real problem.
Yeah. No, that's certainly true. Is it faster than a scooter?
I doubt it.
I know that the bike share program, whenever it was here, that it failed because there wasn't enough demand and like they were getting used to it. But I don't know, like I know the rover's like a pilot program, so it's not necessarily like there was student demand for it. Like I think people use it, probably not that much, but like sometimes people do. But if there was demand for it, I think like some sort of bike share program
Sure.
would have been better to try again.
Like I remember one of the problems for me is like the actual routes it takes aren't very helpful to most students. Because most students, if you're on campus, you're just gonna walk to whatever building you're going. So it's a redundancy that doesn't really need to be used. And like because it's going through like a student section, it has to go super slow because if it runs over anybody, then the school has lost it. So like, part of the problem is like it's too slow to go on main roads, and it can't go fast enough on walkways to make it efficient. It's like there's not really a good spot for it to drive.
Right, so without an independent lane of some sort, it's handicapped by different things. Yep.
One of the complaints of one of my roommates was she was on crutches earlier this year and it was very inflexible. She was on one side of campus and she basically asked the person driving if they could take her to another building on campus, which wasn't technically one of its stops, but it was along the route and they just said no. And so she had to use her crutches and walk across campus. And so I think if we were a little more flexible to what people wanted, or like be like, hey, maybe can you drop me here instead of in a specific spot, it might be a little better.
Yeah, and so that's certainly, that one I wasn't aware of, but that sort of makes some sense. You can also see why they limit that though, going back to the question about buses stopping all over the place, is the efficiency dies when it has too many stops on it.
Yeah, I like program though that you can't, they won't stop unless like they're stopping because there's something around them.
Right.
Like it's pretty different.
I mean, it's kind of interesting to me, like you said, it was a pilot program, the idea was to introduce the largest autonomous fleet. It was probably never intended to make money or really pay off for itself, but you kind of have to start someplace. But in terms of thinking about improvements on that, I guess the question would be, what would be things that you think that could make it better? Either moving faster would be one, going to the light rail station, that would be another, because you're thinking about things that are actually valuable. And the good things to bear in mind. I mean, I'm sure they'll be asking for feedback at some point. And anything you have along the line. For me, I kind of like this one because I could see e-bikes actually playing that role for a lot of the intermediate ones if there's a bike share program. Because they're no effort, just like the Rover is. Unlike a bicycle, we actually have to pedal. The e-bikes are relatively labor-free, and so they've got some upside. Scooters, I'm not quite sure about, but they've been around a little bit longer. I'm going to just kind of flip through this one just because, again, for me, it's kind of interesting just seeing what happened with respect to production worldwide. So you can see China at the bottom. Everybody fell off in the pandemic, so that's not too big of a surprise. But China and Japan are pretty big sizable chunks. If you look at the United States, lighter blue in it, fairly dominant when you go back into the 80s. Very dominant when you go back much further than that. But again, the fall off was pretty dramatic. Toyota and Honda and some of the other ones came in the 70s roughly. And so the upshoot of the Japanese manufacturers was about that time period. Germans have always been around for cycles and things like that. Yes,
Was that representing who was making them or where they were being made?
who's making them?
Okay, so like the Ford plant in Mexico would count for.
Oh, that's an interesting question. I don't know the answer to that.
Right, because there's a lot of outsourcing.
Right. Yes, I don't know the answer to that one.
Okay.
Right.
Right, that's a great question, whether or not it's the location or the company. So I don't know, for instance, if you were to look at Hyundai, what fraction of the production is actually not in Korea. My guess is the majority is still in Korea. So although the production inside the United States is going to be a little bit of an outlier, it's probably a small percentage.
What happened in like 2009, the
Good question.
little,
What happened in 2009?
Yeah.
So that big boost on the other side.
it was like six.
Yeah, so the big jump on part of that is part of the Congress program. So you remember the United States took a large number of cars off the road post recession. And so there's probably a big increase in sales of energy efficient vehicles at that point. Okay. Some of these I'm going to skip through also because I wanted to make sure I spent a little time at the end. Kind of going back to the potential innovations. A lot of this again is talking about what policy has an impact on the way things improve. Because if you take a look at what's going to happen for the US in transportation, a lot is going to be policy driven. So emission standards has been probably the most significant thing that's been done in transportation because it impacts vehicles. It impacts vehicles that are cars and trucks differently. So again, the details are important, but overall, the most important thing is that there was actually emission standards put into place. And the result of it is if you look at efficiencies, and efficiencies improved also. So the axis on the side is for consumption for distance, and that's plummeted over the last couple decades. Okay, so kind of getting into the different things. The first vehicles that came out that were electric somewhat in nature were the hybrids, so the Priuses, were the ones that are probably the most well known. And in the slides and other things you see, they'll be called PHEV, EV for electric vehicles, and P for plug-in hybrid vehicles. So they had a lot of positives with respect to the amount of distance you could travel on a gallon of gas. They were a big improvement. Okay, other things that could be done with respect to making vehicles better. So this goes back to not just electric vehicles or hybrid vehicles, but what are the other things that could be done? And again, it's kind of a nice list of different things. So battery vehicles, BEVs, plug-in hybrid vehicles, hybrid electric vehicles, doing better diesel engines, fuel cell vehicles, different fuels for internal combustion engines, and just improving the internal combustion engines. So really, all the things have been tried at some point. Why would you choose the lower ones maybe to be more important? Or not? So fuel cells, plug-in, and batteries, and hybrids, I guess the lower fourth, are maybe the ones we'll spend the most time talking about. Why those? Because you can make an internal combustion perhaps better. Professor Bogan in mechanical engineering does an engines program, and some of it has to do with improved performance on combustion type engines. So why not those? Why are those maybe not as much of a focus?
They're not reliant on fossil fuels to run.
Right. Not ultimately. Again, the electric vehicles, the downside is that I charge them off a grid that's driven by natural gas and coal.
Right.
But they're not intrinsically reliant on it. If the electricity could come from a cleaner source or a more carbon-free source, then it means that there's non-reliance. So a lot of the focus has to do again with COP26 conference that just happened. Is I want to minimize climate impact, and that means fossil fuels. Again, there's a variety of different things that can be done. When you look at the different alternative fuels, we saw when we looked at fueling stations, the ones that are somewhat common. So liquid petroleum gases, compressed natural gas, and hydrogen were the three that actually had some infrastructure in place. We saw that the hydrogen infrastructure is really, really tiny. Upsides and downsides of the different fuel sources. Let's look at hydrogen as an example. It can be used in anything that generates expansion. So an IC can actually run off of hydrogen. It has to be adapted. Its problem is that if you look at the energy density per volume, it's low. And that'll come from a bunch of different places. It's somewhat important for a car. It's even more important for an airplane. And then again, has to be storage. Emission-wise, it's pretty clean though. And again, for each one of these categories, you can find good and bad things about them. But we saw there's not a lot of infrastructure for anything yet. I threw this one in, was in the book that I started to refer to more as an alternative to our text, the changing energy mix. I mentioned this last class, but I don't think I had a slide in this. I just want to make sure I put this one in. If you look at ethanol, the 5% of biofuels that we use in the United States, 80% of that is ethanol. And the claim has always been made that that doesn't make a lot of sense. This is one of the different forms of justification. You can find lots of different publications online that talk about it, but it does offer some alternatives. So what it says is that the problem with ethanol that I use from the kernels of corn is if I take a look at the top of the chart, it says if I look at the impact of carbon dioxide of gasoline, it's 218 pounds per MMBTUs. And that's, we're just going to take that as being a big number. I don't know what this number's mean at all. But then I look at what happens when I use kernels of corn. And I can see it's better, but it's not better by a lot. And there are a lot of different reasons. So if I get on the chart, I can see that I use fertilizer to grow corn. And the fertilizer has an impact with respect to both production and transportation in it. Farming costs in terms of carbon. The production process, it's a fermentation, there's heat involved, there are different components. And so even the production has a cost. If I do ethanol in a big scale to replace gasoline, there's an overall impact with respect to land use. And I guess those are the main ones. Transportation delivery, so they're about the same with respect to gas and corn. But I can see that using ethanol produced from kernels of corn is not very good. The flip side is stover. So what's stover? It's all the other stuff.
Okay.
Yeah, so when you take a look at that, what typically is considered to be the waste, especially when looking at for food. The stover, it's more abundant to grow. So again, if I take a look at things like this land use impact, when I'm using the stover, there's so much of it by comparison, then it has a relatively small impact compared to just using the kernels with respect to ethanol, which has a large impact because I need more land in that case. Okay, I'm gonna skip past these two. So these were from the text that we're no longer using. They have some nice good simple numerical calculations. And part of the argument, I'm gonna show you in a bit. Okay, so another source, so IEA has got a good collection of different plots. These are separated by country. They're battery electric vehicles and the plug-in hybrid vehicles. So if I were to look at China, the two blue ones, you can see that the latest numbers are that the majority of the growth is because of China. And it's primarily in battery powered electric vehicles, not in plug-in hybrids. So the darker blue is smaller. If I were to look at Europe, those are the two greens on top of that. Again, the darker one is plug-in vehicles. The US, same thing. There's goes from yellow to orange, kind of. And I can see that, again, it's not quite as strong as in the case of China. But again, we're predominantly using battery-powered vehicles as opposed to plug-in hybrid in terms of workload. Relatively, you can see small compared to China. Oh, the other thing about those curves, maybe before I leave it though, is that if you're thinking about this from a math point of view, it looks almost exponential, right? And that's positive because when I want to look at something which is going to become a dominant technology like photovoltaics, the only reason it's grown significantly in the last decade is because the rate of growth is so high that it's near exponential. Same thing with respect to electric vehicles. Now this one's not so much so, and it's the charge stations. If I think about the other thing which has got an impact on whether or not electric vehicles are going to be significant or not, not only do you have to have vehicles, but I have to have the infrastructure put in place. We saw that hydrogen was not succeeding in that case. Compressed natural gas and liquid petroleum gases also were not. And so the hope would be that electric outlets or charge stations was the biggest component of infrastructure we had on that plot. Is how fast were they growing? So if you look at the plot, it's rising, but not tremendously fast at all. It's not linear, it's more than linear, but it's not a rapid increase. What's the other thing maybe stands out about that?
It's interesting to me because so like with China, like China's massive, like the actual numbers are massive, but the growth from 2019 to 2020, I mean China grew more than the rest of the world combined.
Yeah.
Like that is exponential, which is really interesting because I've heard that like China is one of the biggest coal users in the world. So it's kind of a weird dichotomy.
It is. And it's sort of consistent with the last graph where we saw that the number of vehicles also grew very rapidly in the same time frame. Because the number of charge stations went up a lot. And that really is the big point on this, is if you tend to look at the United States and where we've gone, one of the challenges is that our charge stations are not increasing rapidly enough. So we're around 100,000 charge stations over a pretty big country. And so the density is not high enough to have a very positive impact. If you were to drive around Golden as an example for publicly available charge stations, there's probably a dozen in Golden, but not much more than that. So the density is just too low compared to the gasoline infrastructure. So another challenge with respect to vehicles is how fast charge stations are going. That was one of the aspects of the infrastructure bill. Actually, maybe not the infrastructure, maybe it's in the Build Back Better. It's in one of them is charge stations. The state of Colorado also is putting a pretty aggressive program in that area. So charge stations along the interstates are being funded by all things by the penalty that Volkswagen had for lying about their diesel engines. So all the states got different parts. That's actually funding the charge stations going in Colorado. I got this link from David, so I wanted to include that. In terms of,
They were trying to sell me a car, but hey, go, this is gonna be fitting for our class.
you'll have to tell them, it actually showed up on a slide. So this is, it all sounds really cool in terms of words. So there's this Ultium flat pack. It turns out there's still lithium ions. They packaged them slightly different, but no new technology. So going back to the question about EVs in the future, so far everything in vehicles are lithium batteries. So there's no deviation from that yet. A lot of the batteries you talk about in energy storage are for utility scale storage. So the iron air batteries, as an example, or the fuel cells, can't be used inside of vehicles. So they're still waiting for the next step with respect to car vehicles. So even though the GM vehicle has got a cool name on it, still lithium batteries. What's kind of neat about it, Walter, they said that they can actually package in such a way that they can get more mileage out of it. Again, they're not light vehicles because of the weight of the battery packs, but they're claiming 450 miles on their vehicles, 30-minute to an hour charge time, and 0 to 60 fast. One thing that's certainly true of EV vehicles now is the torque in electric motor is pretty sizable. So speeding up is actually not hard.
Oh, I was saying like 0 to 60 in 3 seconds. It's not bad.
Yeah, it's pretty impressive.
Yeah.
And the first vehicle that was supposed to come out now, but is not out yet, is the first Hummer. So
Didn't they
again,
push
kind
it-
of
I thought
a
they
nice
pushed,
choice.
didn't they push it back to like spring of 2022?
That's what I've heard too.
Yeah, okay.
This turns out to be also important down here. That was in the news recently. So the chemistry used for lithium, there's a variety of different chemistries that are used. The ones with the high energy density that contain manganese and cobalt. And so for a vehicle, high energy density turns out to be important. The iron phosphates are typically used in home storage units, but the density is lower, so it means that it's going to be a heavier battery. Why does cobalt has been important in the news recently?
And like all of it in Africa and like hard to get.
Yep, a significant amount. I forgot which country already now. Probably because of terrible geography, but there's the predominant amount of easily attainable cobalt is inside of a relatively small number of African countries. And over the last decade, the Chinese government has bought up a number of those spades. So there's been some pushback on that, is that if the US is intending to be a player in this game, having access to cobalt turns out to be important. And we've kind of lost ground a little bit on that.
In the news wise, I was going to forward it to you. I didn't get a chance to get online. The front page of the New York Times or the Wall Street Journal, I think it was the New York Times, on that very subject.
Yep.
I had, it should be in my inbox. Forward it to him.
Okay, I'm sure if we just type in cobalt in the New York Times.
Yeah,
it'll be the first one to come up. Yeah, so it turns out to be a fairly important thing with respect to looking in the future. This was another part which is really motivational for thinking of electric vehicles. That was a really nice plot. So picking up all the different parts. So this is corporate claims on what they're going to do. So if you look at the light blue, it's in their timeline, when are they going to get to a certain percentage of electric vehicles? So you can see, for instance, if you look at Ford by 2026 apparently is claiming 100% electric vehicles. I didn't remember it being that quick, but I did remember that a lot of the American manufacturers are doing so. And again, going down the line, 2025, so 4 years from now, the sizable number of manufacturers are making a big step in the direction of being predominantly electric. And then going up further, so Volvo by 2030 is 100, plus is going to 100. On this chart, just Ford and Volvo looks like. I don't remember other companies what their claims are, but this is a pretty recent chart, so it's probably pretty current. With respect to introducing different vehicles. This one actually sounds almost hard to believe that Volkswagen is going to go to 75 new vehicles by 2025. I don't know if they've actually got 75 lines, but
Probably Volkswagen audit group, not Volkswagen.
say it again.
Probably Volkswagen audit group, not Volkswagen.
Yeah.
Probably.
Yeah.
It's all the other-
Volkswagen, Audi, and Porsche, and Bugatti, and.
That's
Yeah.
good.
Yeah. And-
So again, you can see a lot of those increasing fairly quickly. Ford's going to jump to 40 next year, they claim. And what are the other things on here? Annual sales, that's probably not what is informative. Yeah, so for me, the one that really caught my eye was percentage of sales. So you kind of see that there's a big corporate move from the producer point of view, but also from the consumer point of view. There's a big list of these, so I just grabbed a couple of the important ones. So a couple years ago, FedEx said that they're going to go to a zero emission vehicle fleet and carbon neutral. That doesn't necessarily mean they're going to be completely off of fossil fuels, but they're going to do a bunch of things that tie into reducing their emissions. Amazon put in an order for 100,000 battery-powered electric vehicles, and they aim to be net zero emissions by 2040. And there's a long list of companies like that. Yep.
There's that thing Amazon was saying they were gonna do, like, for deliveries by drone. Do you think that'd be like more efficient, or do you think it?
That's a great question.
Because
I don't know. I mean, because
Tom,
the drones are going to be electrical,
Yeah.
so that's true.
I don't think they would be because they discharge pretty quickly. Using those motors.
they wouldn't be
Yeah.
able to carry it.
Yeah, especially carrying weight. they discharge.
Right, so by contrast, like a train, where the ratio of freight to vehicle is pretty high. Probably drones not that high, but I don't know the answer. It's an interesting question, is how that compares up. Again, it's probably another one of those ones where if you look at that plot of how far people drive, depending on the distance of delivery, will have an impact too, because drones probably have a limited range. Okay, another good chart. So I've just been trying to gather hopefully stuff that you'll find useful from a reference point of view. Is if you look at all the different sorts of potential ways of powering a vehicle, not only do you have to look at the fuel that it's using, but also the energy to produce it, the overall cost of its life cycle. So this is a study that GREET stands for Greenhouse Gas Regulatory Emissions and Energy Use and Technology Model. So there's a whole website associated with this at Oregon National Laboratory, and they've got it's not a spreadsheet, but they've got a program you can put numbers into, and the idea is to calculate how good is a vehicle over its entire life. Not just does the fuel it burns generate relatively small amounts of carbon, but what's the overall impact based on the components that go into the system and all the other pieces of it. So down here is a car. So gasoline conventional internal combustion engine is 409 grams equivalent per mile driven. So again, much like an LCOE, I do a normalization by the amount of product, the number of miles that the vehicle drives within its lifetime. And I get a number. So that's my baseline for comparison as I go up. And that could go up. So at the very top, for instance, you suppose I have a battery-powered electrical vehicle with driven by renewable energy. And actually, I'm going to take that back. Based on that being zero, it means that this chart must just be the fuels. Because for sure, producing the BEV is going to cost you energy. And unless it normalizes out, which I don't think it does. So this is probably the fuel impacts on it. So renewable energy, there's a couple places I've got zeros. I might look at other places though, and I can get to low value. So for instance, diesel for biomass gasification turns out to be fairly small also. So there are other alternative fuels that have round trip efficiencies for the carbon. So the overall impact can be small as well. So this is a great chart in terms of identifying what are good and bad ideas for different parts. The other part, which actually wasn't on this chart, now that I look at it, is this other part. Is if I take a look at the effectively the energy cost of manufacturing something, is how do they compare? So this is going back to the book I mentioned at the beginning. So these are the manufacturing costs and the greenhouse gas emissions for different sorts of vehicles. And so the categories are broken up over there. So there is the body, the powertrain, the transmission system, the chassis, all the different parts going up. Like you imagine, whether or not it's a gas-powered internal combustion or a plug-in hybrid vehicle with a 40-mile range, I think it was a 44 response to. These are 130-mile ranges for the battery-powered vehicles. Those lower categories have to be largely the same. And so there's a lot of resemblance as I go down towards the bottom. If I go higher though, I could see a 300-mile range battery-powered electric vehicle actually has a fairly large impact from an environmental point of view because of the batteries. So looking at it from this point of view, the carbon cost of manufacturing a battery-powered vehicle is significantly higher. Okay, now is that a problem? Because this is in tons of carbon dioxide equivalents for a battery-powered vehicle. So I'm talking 10,000 tons. 10 tons. So 10 times 1,000, so 10 to the fourth kilograms of carbon dioxide equivalent.
I guess initially it seems bad, but maybe when you think about the gasoline cars, like the initial like carbon production might not be bad, but they're going to continue to produce carbon throughout their lifespan. Maybe it's not as big of a deal as it seems.
Yeah, that sounds very reasonable. In a lot of ways, if you think about that, it resembles a lot like the LCU calculations that we did. Is that when I put in photovoltaics, the initial capital cost is very, very high. But because it has no O&M costs, or significant O&M costs over its lifetime, when I look at the levelized cost of energy, then it's quite low. Same thing with respect to the carbon calculation in this case, is that the initial investment in the battery-powered electric vehicle is quite high. But because the equivalent of the O&M costs that we did in the LCV, the fuel costs are quite small, then over the life of the vehicle, and again, it's normalized by number of miles. So this again is 10 to the fourth kilograms of CO2, but we're traveling hundreds of thousands of miles. And so when I normalize it out, the contribution is relatively small in the end. And again, it's not that simple of a calculation because the payback's different. It has to be done in the same way. Okay, I had mentioned a paper that I really like called the 50 states model or the 50 state solution. It has a bunch of names by Mark Dickinson from Stanford. In it, he doesn't include biofuels. And that's kind of strange because I tend to think of biofuels as being a renewable resource that's of value. But he said, especially in the case of transportation, biofuels don't fit. So he's going to do hydrogen or electric powered vehicles of all sorts, whether we're talking planes, boats, trains, all of those. And this is his justification tied in with it. So I've got a reference to the paper that this came out of. The reason they don't include it, WWS stands for wind, water, sun. The three things that he considers to be energy sources. If you were to take a look at the change in CO2 emission associated with different things, if I do a battery-powered vehicle where the energy came from wind, I get a negative 40, almost as much as I could possibly get in terms of reduction compared to the baseline, which is a gas-powered vehicle. Same thing with respect to these other ones, customers hold power, photovoltaics, wind. This is wind with a hydrogen fuel cell vehicle. So all those are really good things, as long as the energy produced is produced by wind or solar of some sort. When I look at ethanol, so the most common biofuel we have in the United States, it turns out it actually costs me relative to gasoline. And so the net change is actually negative. So that's one of the things inside of it. The other one that you mentioned is the amount of land use. And so if I put in turbines or concentrated solar or photovoltaics, it has a net positive impact on land use compared to fossil fuels, but it's relatively small. If I start looking at biofuels, in this case specifically ethanol produced from corn, probably the worst case situation, so probably ears of corn, then it turns out to have a very negative impact too. So his argument was Don't use biofuels that are liquid because it costs you land. It actually leads to the greater number of deaths. I didn't actually put this plot on here, but that's in the paper also. Primarily because of air pollution. It has an impact on the water supply. And again, air pollution is a factor. I don't necessarily agree with this 100%, but you can kind of see the arguments that go into making decisions about fuel sources. Okay, past that. I'm going to skip past that one too. Okay, so again, the last set of slides are more to do with maybe the top talk, which is more innovations and different uses. This is the one I think that everybody's been reading about for a couple of years now. Is what do you do about all the semis that move freight? Because we saw it wasn't a big part of the picture, but for sure there's a contribution with respect to moving freight, and that looks like an unsolvable problem because we tend to think of the gas stations that line all our interstates as the way that things move across the country. Those 2,000-mile trips. So Elon Musk came up with this idea, and other companies are as well. But this is probably the most publicized one. Is the idea of the Tesla Semi. Numbers look pretty good on it. So again, not lightning flash by comparison, but again, 20,000 pounds after it, so 40 tons per load. It takes a bit to get that moving, but again, 0 to 60 in 20 seconds. It can go up a 5% grade with a reasonable speed, so it doesn't stop, and a range of 300 to 500 miles. Before I move on, because I don't actually have the slides here, what is charge time for a vehicle? And it depends, right?
Yeah. Like,
So-
like full charge?
Yeah,
or
so
like-
full charge.
Like 8 hours?
Right, so if I'm at the one that they tore out of the lot in CTLM, that's probably a 10-hour charge in a typical small vehicle like a Leaf or a Tesla. What's a fast charge? It's actually shorter,
2 hours?
so it's about an hour. So it's a DC charge, the circuit is completely different, it charges light-duty batteries, but you could charge in about an hour. Still kind of long. 30 minutes is actually what I've heard also, 30-minute charge. But 30 minutes compared to filling up your gas tank is still a fairly sizable amount of time, especially when you're going across country and you're recharging every 300 miles. So you've got 7 fills going across country at least for doing something like that. So 7 fills in an hour each is a good part of a working day. So still not perfect. What's remarkable for me about this, and again, I didn't look at this in too much detail because I've never been interested in buying one of these, is that they have a lot of motors on each one of the axles, so it's got a lot of torque and power, which is how it does that speed and acceleration. 2 kilowatt hours per mile. How does that compare to like a Tesla or a Leaf? I don't know if anybody knows off the top of their head what mileage is on this.
I have no idea, but it's probably not really good.
It's surprisingly good.
Oh,
So, again, I don't know anything about semis. I don't know what the gas mileage in a semi is compared to a car. But my Leaf gets about 5. So it's not dramatically different, surprisingly. And then this is also their calculation. So this is Tesla numbers coming out. Is that their estimate is it's actually relatively cheap. The number they published was that it's comparable to a diesel truck. Their assumption is based on $2.50 per gallon. Because it turns out a gallon of diesel is significantly more expensive right now. And electricity being about 7 cents. 7 is about right still for purchase at large scale. So again, it looks promising. There aren't any yet. So they're also intended to be out. I think there are prototypes that are in operation, probably full ones, but in terms of nobody's taking delivery on it. I think Pepsi's got the first bunch that come out. This was from a previous one. I think we talked about this briefly a couple classes ago, so I won't say too much about it. The cool thing about the autonomous ones is that if they're actually fast, they don't travel 11 miles per hour. And they don't hit each other, which means that they have to talk to each other, which is a problem that the Tesla currently has right now in the full automation mode for the Teslas at this point. But if they have those things, the ability to communicate with each other and also with objects, then they actually can be made fairly small. So there is a big argument made for small fleets of autonomous vehicles that are very light. So then again, if you've only got 1.5 people on average for a vehicle, which is the numbers we saw earlier, is that having a 2-person vehicle that doesn't have a driver inside of it and is very, very small is actually a good picture for the future. So I put that in there. And again, I'm in favor of it. I can see it's probably not a long-term project for mines. It'll be replaced by something else, but it's again kind of an interesting idea. If nothing else, is a demonstration. So I don't know the details that the accident is in, but it's had relatively few accidents.
At least one.
At least one. And is again, more also a demonstration
Yeah,
project
it
at this
did.
point. Does everybody know what happened?
Somebody just ran into it. at the
Yeah,
wrong time.
So
Yeah.
we're on to the back.
I heard it was like right before, or like, basically what I saw, was like right before, right before. You were? Oh, God.
He was young.
I
Okay.
think the person probably was paying attention.
Now, again, we saw that air transport wasn't a huge one. And what was the other thing maybe as a takeaway about air transportation? So this is our projection on what has to get better, but forgetting about this, what would you say about air transportation as an area that you want to focus on?
Yeah, I was kind of interested, they have those, like, plans for the jets that basically can take like 20 people. What was it, like New York, Tokyo, like 12 hours or something? It's like, it's an interesting concept. I'm curious how the energy would compare, because like, yes, you're going a lot faster, you're also carrying a lot less people.
Sure.
You're gonna need a lot more force to move it.
Yeah, I suspect it's probably pretty terrible. I mean, I don't know the numbers on it, but it's because the part you're trying to normalize to, which in their case are making an argument in terms of travel time, doesn't help in energy efficiency.
Yeah.
So I think you're right that they're low. The thing that, which again was sort of a takeaway that I want you to have with respect to air travel is two things. One, it's actually relatively small. So it's about 8% of the transportation energy. So you'll have an impact if you improve it, but it's not a huge impact. The other one is that because they've managed it really, really well in terms of packing planes, is that the efficiency of travel is actually better than a vehicle if you look at it normalized per passenger mile. So that means when we think about what can we do in terms of transportation in the future, there's parts of it that have to be modeled after what the airlines do. Is that if you could pack, so you're running at capacity all the time, then you can get down to efficiencies in terms of the energy intensity that are comparable to vehicles. So this is kind of what they are looking at. They said things have gotten better. So when this book was written back in actually, I don't remember what year this was published, I guess 2011. They were better, but the question is, what did you do past that? So this is projections on what has to happen. So again, the vertical axis, bottom axis is time. They've got projections of, in order to reach goals like 2 degrees change in temperature, so sustainable outputs on net zero. This is what they predict has to happen. Looking at this axis, this is megajoules per RTK. RTKs are again weird units. They have to do with the fact that you don't just count passengers when you look at these, because these things are always carrying freight also. So it has to be normalized to volume to some extent. So there's again a weird combination. It's a metric ton of revenue load transported 1 kilometer is one of RTKs. Don't worry too much about it. It doesn't translate into passenger miles exactly, but it gives me an idea of where do I have to go. So from where we are now, someplace around here, it has to get better by about a factor of 2. And to get an idea of what the rate improvements would be. So this 3% annual decrease is what the goal are. We've realized about a 2% decrease over time. So there's a fuel efficiency part at 1.3 that's mentioned up top between 2014. That wasn't because fuels got better. It was mostly because planes got newer. We know that Boeing's run forever, but as time goes by, the designs get better. And so better plane design, better packing inside the plane, better utilization of space. All those things have driven that down, but that means at some point you reach a limit. You can't fit more people inside the plane. And so those last bits have to be by some other means.
The supersonic jets that United said they're gonna buy
Mhm.
claim that they run on biomass kerosene and are therefore carbon neutral.
Right.
But
Yeah.
I doubt that.
Yeah, so that's the other question is whether or not biofuels make sense. Again, Jacobson says no. And but there are some arguments for doing that. To some degree, it's going to be the same sort of question as when we looked at ethanol. Ethanol is kind of okay if it's the stovers. The problem is when it's the kernels. And so if we look at different ways of producing biofuels, there may be, at least from a carbon point of view, and at least what we're doing, there could be other issues. So land use and health are examples of things that might have a negative impact. So I think it's to some degree an unanswered question a bit. There's a lot of interest in doing that though. So there's the website up top was one that I found was looking at these targets. These are the organizations that are part of it. So you can see a lot of the big hitters on United, UPS, FedEx inside of it. And they're looking at trying to do this. They're not necessarily going to do it by getting rid of jets. So again, they're looking at things like biofuels as one alternative, other efficiencies you can get. So these sustainable aviation fluids are primarily biofuels. There is a problem with it though. It turns out jet fuel is a lot more complicated than gasoline. And so the manufacturing of jet fuels turns out to be harder. Some of the biodiesels are close, but they're not optimal. And so there's research papers, this one that I've got linked up here is an example of they understand the chemistry, but it has to be done. They just can't do it inexpensively yet. Okay, so these are more speculative things. We talked about, I think, one of these before. And so again, I just popped up a couple of interesting pictures. Propellers turn out to be part of the solution because then I could use fuels that drive an electric motor. Or I could use a standard ICE using biofuels. I might lose something in terms of speed. So when I look at these, that guy was the fastest pure electric plane, and it only went a little less than 400 miles per hour. So kind of pokey by comparison. This is one that's actually got a V12 gas engine inside of it, and this is one we talked about before. It was trying to solve that problem. We looked at cars. We said that there's a loss because of aerodynamics. And so in cars, we don't deal with that too much, although we do to some degree. So things like, for instance, the mirrors on your car and the shape of a lot of pieces are tied in with that. Even the height of your vehicle above the ground causes some problems. But you can go to extreme in a vehicle like that and optimize the aerodynamics and get some more range out of it. So these are two that were in the news recently of things that are electrical / renewable with respect to flight. They tend to be small. But again, one of the upsides is that if you do that calculation about the cost per passenger mile, even though the number of passengers is small because the vehicles are smaller and the amount of fuel use is decreased, they also still come in at very, very effective compared to cars. A couple more in that line. So this one is from Urbana-Champaign, kind of a highly speculative idea of using hydrogen, where the wings are the fuel tanks, just like airplanes now, but you need bigger wings because you need more space. So designing the fuselage and the wings, and then also setting up the parts. So this is a fuel cell hydrogen-based plane. It looks like it will probably work. So again, I've linked stuff at the bottom. What's the downside of a hydrogen one now? Based on what we've talked about so far. Fueling stations would do it. So I have to get a lot of capacity to make sure that I've got the range I need. So again,
Having done a history degree in the past, I gotta say the Hindenburg. Terrible tragedy there.
that's probably what people think about.
Right. I would think they'll have these well contained and hopefully no leaks and no sparks.
Probably. I guess probably you worry a little bit about when you land and take off, which is always a scary part on all of these. Certainly anything that happens up at several thousand feet doesn't really matter. But I think you start to say also the production of hydrogen, which is what we're looking at. Until we actually start making hydrogen with an electrolyzer, then there's no net gain. And then that one was a hydrogen fuel cell, but it was driving a propeller. So a lot of the ideas for advancing planes are dealing with jets because the fuel is too difficult at this point. For transport, international transport, IMO is the International Marine Organization. They've got a timeline on things that they're going to make better. And so I'm just going to read off a couple of them. So they've got a plan. And so their plan has to do with improving energy efficiency, better management on the ship for more efficient operation. This is not a plan, this just says greenhouse gases. And this is it's actually just an organization. Yes, I guess it's really those two.
I was gonna say, that's the key.
Right. So the two things are increases in energy efficiency. So they're still probably going to use the same fuels, but improve efficiency and then just overall management. The same sort of things we talked about why airplanes have gotten better between 68 and 2014 isn't because the fuels got better. It's the planes got better, so they became more efficient and they managed the way they managed freight better. So the goal is to do some of that with respect to that. I'm going to go back to sorry, I got this in the wrong order. So this is another plot which is looking at what's going to happen with respect to fuels. And this is coming from EA. So the two things on here that, let's see, I'll put those legends down here. So these are fossil fuels. So this is now, and everything's a fossil fuel. The amount of low carbon fuel share is pretty much zero. And then the darker blue is lower zero carbon fuels. So again, kind of unspecified what they are. But with respect to what are the things that we have to do in order to reach some goals that they set by 2050. And these are two different pictures. So this is sustainable development. So this is kind of where do I have to get? In order to get there, it has to be about 50% fuel. So they're going to still be in 2050. They're using standard fossil fuels. But that plays about half of it in order to reach those goals. Okay, so these are the ones from the older book that I still kind of like. Is one thing that you'd like to do is scale. As you make the ships bigger, then the net efficiency per load improves. And so you can kind of see as a function of time how fast ships have increased in size. This one I don't think was actually built. So in 2011, it was a proposed ship. But the Evan Gibbons was built. So it's 220,000 gross tonnage. So it's not quite as big as the freighter was supposed to be, but it's pretty large. What's the Evan Gibbons famous for? It was the one that was stuck in the Suez Canal.
Oh, okay.
So again, you can see the idea. They needed to make it bigger because the efficiency improves as the ships get larger with respect to shipping. It's downsized since the Suez Canal. Two more ideas that paper had that were sort of a little bit innovative. One of them was go slower. Because we know that aerodynamics and drags are all a function of velocity. And so if I'm not in a rush, I don't have to be on the other side of the ocean and put away. Is that decreased speed will actually improve things. The other cool one that I like, or these two pictures here, is putting a sail on it. So they'll never be pure sail boats, but you can certainly get a wind assist, and that'll improve the energy efficiency inside of it. And then third is vehicle power. So we do it in subs already, is that cargo ships could conceivably have the same sort of impact. Okay, I don't think I'm getting more slides on sea transport. So I'm just asking you, what do you think you could do better with respect to freight that moves across the sea?
This isn't necessarily like improving ships, but like central or like decentralization of like the economy could help because then you don't have to transport as much stuff.
Yeah, so local production
Yeah.
would be a good example.
I mean, they're saying once the North Pole melts, you'll be able to transport.
Oh God.
So,
There will be some short distances.
that'll make everything more efficient.
It's kind of intriguing. If you ever looked at the flight paths when you fly back from Europe, a significant number of them actually go fairly far north. just to shorten the path. So that probably would decrease. So I'm not sure how much though.
Amphibious freight trip. And have them crawl over the land instead.
Yeah, in amphibious type vehicles. The challenging part about that would be making one that's as big as the ever given to crawl over top of stuff.
Use like those giant like amphibious landing crafts that the Marine Corps uses. They don't like them anyways.
Right.
So,
Yeah. Other things you can think about with respect to ships. Airplanes is a tough one. Biofuels is certainly a direction that's worth taking a look at. Prop planes with different sorts of motors and fuels inside of it. Still a little bit of an issue. But again, in the Stanford picture that he envisions, it's hydrogen fuel cells with turning props and no biofuels. So air flight is difficult, smaller, efficient, and electric is likely, and hydrogen would be the other. With ships, hydrogen actually becomes a little more feasible too. So it's not on the list here. But then storage volume isn't as big of a deal as it is in the case of an airplane. But again, the other challenge is that then you're traveling huge distances, so there's no intermediate spots to fill up. Okay, so that's sea transport. The last two slides that I put in specifically for David.
Oh, thank you.
So this is, again, a nice plot. Is if you look at the vertical axis, it's grams of CO2 equivalent per ppm. So again, this is another one, so we're giving this as a combination of distance and freight, whatever you're moving. So if I look at that, on this particular plot, so there are a couple things. Yellow is the greenhouse gas intensity, there's a range. So it's not a fixed value, it's going to depend on a bunch of other factors. There are two specific dots that correspond to the values when you're staying urban, so you're within a city region, and non-urban is rural. So the constraints are a little bit different with respect to that. If I take a look at going across vertically and which ones are lower, rail is actually quite thin. And again, this goes back to the steel wheels that roll on relatively flat tracks in terms of transport, and the fact that they're massive, much like the large cargo ships. Trains never move small amounts of stuff. And so when you've got a large volume, relatively low resistance, and I took a look at the greenhouse gas equivalent, using standard fuels, it's again very, very low. So it's the area that I maybe have the least room for improvement to some extent. So what could I do? And again, thinking about this, I sort of want to focus in here, because that's 2/3 of my energy costs for transportation. But I can always try to tweak everything else a little bit. So air is 10%. If I can get that better by 50%, then I cut off 4% in the overall picture. Rail is not that huge yet. That could change in the future. But again, I can maybe improve things a bit. What would be things you could think about to improve rail? I don't know if I've got something on the next slide because I can't remember now. But thinking about what are the things that you could actually improve with respect to rail transport?
Is rail transport like train? Is it a train like that?
It's three of them. It's the long distance trains, so cargo over distance, but it also includes, I think, transit within the city that are rail based.
Okay.
And that's probably part of the reason for the range is you look at the upper end. Rail transport inside of the city, not that common like the light rail, is not as efficient as the bigger ones. Yep.
I don't know, but how, like over the years, how is the efficiency of their diesel engine for rail? How has that, has it changed much over the
That I
last,
don't know.
70 years, 80 years?
It's improved quite significantly. It's been a big push. One of the nice thing is you can control how many engines you have online compared to what you actually need, and that's been a really big push over the past couple of decades, especially when we had the fuel spike back about 2006, 2007. It was pretty much ordered that you only had a sufficient number of engines on for the horsepower you needed to get over the road, which may mean you won't be able to go track speed, which disappointed a lot of engineers that like to run trains like sports cars. Because you're consuming a lot of energy for no need for speed, because chances are you're going to get stopped before you come into the terminal anyway. So slowing the whole velocity down doesn't really affect delivery, but it greatly reduces the fuel consumed.
Makes
I
sense.
still surmise if we put catenary back, we can use a multitude of generating sources and run the trains on renewable energy, but you have to have expensive infrastructure of passing the electric to the train.
Yeah, so that would, when you tend to think of putting renewables, things like wind and solar, you tend to think electric. And then you would have to actually deal with transmission and power. So that would definitely be a limitation. But yeah, I mean, that's a good question, because if diesel had not improved very much over the last century, then there'd be an opportunity for gaining at that point, but it sounds like it has.
And they could probably gain more, there's a lot of research going on that.
Okay, let's see my last slide. What's it tell me? Oh, yeah, that's right. So things that people are looking at and directions that they think the things are going to have to go. So it turns out actually in rail, there is some investment in different things. Electricity, like was mentioned. So the dark blue is, you can't read it, electricity and hydrogen. And this is oil. So in terms of where are we right now, in terms of the global picture, because this is from EIA, from IEA, the other one, is that we still have a fair amount of electrical rail in place already. Not as much hydrogen, but it's coming on. I just picked a couple examples that a lot of these projects listed. So there are some hydrogen fuel cell vehicles, both in Germany and India and a couple other countries as well. So it's one that's being looked at. Again, the downside is the hydrogen's from the wrong place. But at some point in the future, the hydrogen infrastructure might exist, and then that becomes a feasible way of doing things. It's still not as good though, because again, the downside is if you look at the efficiency, the fuel cell efficiency is quite good, but it's actually the electrolyzer efficiency is fairly poor. So it'll never be as good as directly running on electrical, but storage is better. The other one though is different sorts of electrification, which means they have to transmit power. And that's again being put in place. India's made a plan of electrifying a lot amount in their case. There's a lot of rail traffic in India. It's also moderately compact as countries go, because their population density is relatively high, so it doesn't make sense for them to focus on that. So those are sort of the only directions I think that I saw with respect to rail. I didn't see anything broader with respect to renewables specifically. There's not a whole lot to do compared to things like perhaps even ships. Okay, so that was my last slide.